this is the really simple molecule. You see the 3 carbons, 6 hydrogen, 1 oxygen. That's a molecular formula. Just the 3 carbon. So, as I said, when you see the carbon 13 NMR, what you need to pay attention is how many peaks there. How many peaks here. But that's a TMS. That's basically the reference unit. We'll count that. 1, 2, 3. So we got 3 peaks for the 3 carbons. So that sounds like we don't have any symmetrical molecule. And then, as I said, these ET games, that's how many peaks it will be split if we allow the splitting to happen. So this is a decoupled spectrum. We do the decoupling, so single peak for the single carbon. But if we turn off the decoupling, this peak will turn to doublet, that peak will turn to triplet, and this will turn to triplet. What does it mean? This has a 1 hydrogen, that's why it becomes doublet. And this carbon should have a 2 hydrogen, that's why it becomes a triplet. And that carbon also should have a 2 hydrogen as well, right? So that information is going to be really useful. So what else we should pay attention? The chemical shift, right? The chemical shift, these peaks are 138, something like that. That's between the above the 110. So these 2 appears in a range where the double bonded carbon appears, right? We don't know it's going to be aromatic like a benzene, but we can easily eliminate the benzene because there's no way you can make a benzene with a 3 carbon, right? It's got to be double bonds. And then also, if you do the degree of unsaturations, then you can calculate the degree of unsaturation from the formula, which is given here. So the formula for the degree of unsaturation, number of the carbon, you think of the half number of the hydrogen, right? You take off the half number of the hydrogen, but you add half number of nitrogens and plus 1. So that will be 3 minus 3 and plus 1. So there will be 1 degree of saturation here. So that 1 degree of saturation, but that could be either double bonds or single cyclic structures. But we know it's double bond because we have a peak showing up here. That's the double bonding carbon shows. So these 2 peaks at that region, meaning that we got 2 carbon, these 2 are making double bond. Right? That's what it is. But we also have another peak showing like above 60, and then that's a triplet. So this carbon should have a 2 hydrogen, but not only that, that seems to be de-shielded further from this normal carbon range. So that means that this carbon should have electron withdrawing groups. And then what electron withdrawing group we're talking about here is an oxygen. So this carbon should have an oxygen in order to pull down this far. Otherwise, if there's no oxygen, this carbon peak should be over here. So if you see the peak moving down between the 60 and 90, that typically means that that carbon has an oxygen bond to it. And then this is a double bonded carbon with a 2 hydrogen. This is a double bonded carbon with a 1 hydrogen. There's a 2 hydrogen there and bonded with an oxygen. So I think we found out all the carbon, right? 3 carbon we found, 1, 2, 3. And then there are going to be 1 oxygen. We found the 1 oxygen there. And then we have to find 6 hydrogen, 1, 2, 3, 4, 5. So 1 hydrogen is missing. We still have to find the 1 hydrogen. And then that's very easy to be placed as an alcohol. So then this will complete the structures by putting it together, right? These 2 has to be put together, and then this end has to go there. So you will have the molecule, structure of the molecule that will give out this particular carbon spectrum. So in a way, this is the problem solving of the carbon 13 NMR. So pretty similar to the protein NMR. You just have to use a different numbers. And then, yeah, basically, Anyway, these are pretty simple ones. The next one is still not that big. It's a 4 carbon, 6 hydrogen, 2 oxygen. What we see here is we have a peak at 180, and then that's a singlet. So 180 means that's typically the carbon of the carbonyl. And then carbon of the carbonyl don't have a hydrogen there, so that's why it becomes a singlet. That totally makes sense. We don't have any signal showing between the 110 and 150, so that means that we don't have any double bonds, right? We don't have any double bonds. And then if you're just wondering, I guess we should first thing we should do the calculate degree concentrations, right? So 4 minus 3 plus 1, right? Oxygen doesn't do anything for the degree concentrations. So 4 minus 3 plus 1 is 2. So we have a 2 degree concentration in the molecule. And then we just found out the carbonyl. So one of the degree concentration is actually coming from the carbonyl double bonds. Yet we still have to find out the one more degree concentrations that typically comes in double bonds, but there's no signal coming out here, right? So what does it mean? There's no double bond, yet we do have one degree concentration. Yeah, that actually comes from this accusation. The ring structures also increase the degrees of concentrations. So this is a cyclic molecule. The cyclic molecule with a carbonyl there. Let's look at the other side. We got 2 oxygen. 1 oxygen, it's a carbonyl is having that 1 oxygen. We have to place another oxygen somewhere in the molecule, right? And then that's probably what it makes it de-shield it out. This triplet carbon at like 70, that's the carbon probably having the oxygen. That's why it's pulled out. And the other 2 carbon here, that's a triplet, but it means this is H2, that must be CH2, this must be CH2, but those 2 carbon shouldn't have an oxygen, right? Because otherwise it will be over here. Being down there means those carbon shouldn't have an oxygen. This one does, by the way, right? You can see that, it'll make the peak move. So, put it all together, we got carbonyl, we got CH2 because it's triplet, but I put an oxygen here because it's a de-shielded. There's CH2, I put those things 2 there because it's triplets. Then let's find out what we're missing here. So all together, we got 4 carbon, 1, 2, 3, 4 carbon. So we found all 4 carbon here. 6 hydrogen that we need to find out, 2, 2, 2. So we found all the hydrogen. And then we need to find out 2 oxygens, 1 on the carbonyl, 1 on there. So we actually find everything. So all the pieces are there. Now we gotta put it together. So this question, I like it because this is a question that you have to think about how to put the pieces together. It's like a jigsaw puzzle. I mean, of course, simple jigsaw puzzle doesn't matter, but you got like 100 pieces or 500 pieces, 1,000 pieces, depending on where you put the pieces. If you put it one wrong, it's going to mess up the other parts, right? So if you try to do that and it doesn't add up, then you got to think about you must place one piece wrong in some other places, so you got to check back again. So how to put these 4 pieces together? How many different ways can you do that? Well, I guess that will be the exercise you're going to do. But let me point out one particular way you can put the structure together. Carbonyl have 2 bonds to make, so I put 1 here, right? I mean 1 there. I connect the other one over here. I put the oxygen here. I put it over there. So that will be the one of the possible products by putting these 4 pieces together. Is that the only way? Assemble 4? No, there's another one. I just have to switch this one up and down, then you're going to have different structures. So even though you find the right pieces, if you connect them wrong, then you could clearly get a wrong answer. Of course, you will deserve a partial credit, but it won't be the right answer. So how can we figure out which one of these 2 is the correct answer? Exactly. So you actually listen to me. So that was a kind of things that once you kind of get to the conclusion, if let's say you believe this is the molecule to give out the spectrum, then what I want you to do, check your answers by trying to anticipate what will be the spectrum of this. I mean, the carbonyl will show the same region, so I don't think that's wrong. These carbon should be one of those two. But these oxygens are connected, not only this carbon, but also that one. So meaning that these two carbon should be done, you're gonna be two peaks in this region, not two there. So if that's the answer, you got a two carbon having one oxygen, you got two peaks here, one peaks there. The patterns are different, depending on actual what the structure is. You see that only one peak, D should be this far. That means that only the one carbon should have an oxygen. And of course, this carbonyl might have shifted down a little further, but it's, that's not a different issue. This is a basic reason we're talking about these three carbons. And then only the one of these three carbons are usually, and then these structures are only way you're going to have a one carbon having an oxygen bound to it. So that is what you need to do to figure it out. Finding peace is a critical. You got to do that right without errors. But after you do that, how to put them together is another thing. You also have to get it right.